And hello. Today I'm going to make another UOM example. I think the last one was a little bit complicated because we were introducing what this is like 4, 5, 6, 7 units, and I was trying to explain the intricacies between the thermodynamic temperature and thermodynamic temperature interval. So it's a lot to cram into one video. Um, yeah, there's a good chance you might not get all the intricacies of using UOM. So I'll try to start from a simple example, hopefully to help aid your understanding. All right, now this is a fantastic package. And I have not quite shown why it's that good yet. So let's start. Let's start again. Okay, what I'm gonna do is I'm gonna make a new I'm gonna do theory again. So I'm gonna copy and paste this. I'll paste it here. There's or rather, is there a copy and paste? Okay, so I'm gonna rename this as ideal and ideal guess. Okay, I'll just call this ideal guess. I don't want to do real guesses yet, so if not, it will be too much. Okay, let's do this. I'm going to delete all of this, and I'll just say ideal gas equation. So what's the equation here? Okay, I'm just going to delete this. And what's the ideal gas equation? Okay, there are many ways you can write it, but the way that some might be introduced, PV equals to nRT. That's the first way. PV equals to nRT. So pressure times volume of the gas equals to number of moles times the gas constant, and then T. Okay, T here is temperature, and it has to be in Kelvin or Rankine. Okay, thermodynamic temperature. Okay, it's not a temperature interval, it's a thermodynamic temperature. So again, there must be that difference. You substitute, if you substitute T in degree C, you'll get the wrong answer. Okay, this has to be in Kelvin. So very strictly in Kelvin. Okay, so this is a thermodynamic temperature, right? Okay, what's the other way? You might see this online. P, let's see whether I have a tilde V. Do I have a tilde V? Okay, I can't remember how to have a tilde. Okay, this is a LaTeX thing. Let me go and find the correct syntax for this. Because I'm used to doing things in LaTeX. More used to that than Typst or Typst. Okay, so the way you do tilde is quite straightforward. Just tilde with a bracket, and then you put your word there. Okay, so there's no backslash. Just put tilde with V. Okay, PV equals to RT. Okay, PV equals to RT. Okay, the second way is actually where the volume here is a specific volume, or molar volume. PV equals to RT. So again, this is the ideal gas constant. This is temperature in Kelvin. Or Rankine or what. This has to be a thermodynamic temperature, but I just put Kelvin there to indicate that okay, this has to be an absolute temperature scale. Okay, if you divide both sides by n, and you define the molar volume as in volume per number of moles, okay, that means one mole has this much volume, you will get this V tilde here, which is the molar volume. Okay, PV equals to RT. Okay, pressure times volume per number of mole equals to the ideal gas constant. I can't remember what the exact name was, but yes. Yeah, and then thermodynamic temperature. So PV equals to RT. Okay, so generally speaking, there are a few things you want to find out. If you have the volume, you need P and T data to get your if you want to find volume, you need your P and T data. If you want to find your temperature, you need PV data, so on and so forth. So, right, that's what you need to do. We'll have functions that we can actually obtain several things. Find volume, you know, find you want to find the temperature, you want to find pressure. Okay, so let me close this. So ideal gas is pretty straightforward. Okay, how do you code functions for ideal gas? So I want to introduce you to something since we usually need to do it anyway. Okay, I'm going to introduce you to some functions that actually take in values, but I'll do that in a while in this video. But okay, let's just move on. Let's make a module called ideal gas. Okay, what I'll do is I'll use, and then of course, let's see whether there's a quick fix here. Control dot create module ideal gas. That will make the ideal gas module. Use create ideal gas. Use everything within it. This is the pattern I'm used to. I'm going to go to the ideal gas. Okay. Yeah, I'm not going to use my mouse since I've been key bindings, but yeah, I prefer use Vim. But anyway, ideal gas. I'm going to make a function here, right? I'll make a function here. Make sure it's public function. It's a public function. What do I do with it? I want to get temperature, for example. Okay, so normally this is how we code our functions, right? We don't give it any inputs or outputs, right? But functions are supposed to at times give you outputs as well. So how do you specify the output type? Okay, well, if you want to specify output type, use the arrow as such. This dash and then the greater than sign. Okay, if you want it to be a float 64, you define it like so. Okay, and then this is how you do it. Of course, there's a problem here. There's a problem right here because it says the function get temperature. When you try to return an F64, well, you're returning this open and close bracket. Open and close bracket is just means it's returning like a nothing. It's a void. You're not returning anything. That's the easiest way to understand it. Okay, or the simplified way. So actually, if you even if you return some random number like 5, okay, return 5.0 and colon. This is how you actually return the value. Even if you return a random value, yeah, now the thing will actually compile. Now there are two ways to return. This is one of the ways which you explicitly state return 5.0, or you can just type 5.0 like that. Both are acceptable within Rust in this version. So sometimes I like to do this because it gives me the feeling that I'm returning something. It makes it very explicit. Also, so I'll just do it this way, but just know that if you do it like so, this is also acceptable. So there are two ways of actually returning values from functions. Now, I don't want to return F64, I want to return thermodynamic temperature. Okay, now just tap enter and make sure this is your SIF64. I like to return in a float 64 type. I'll save it. Okay, so the thing about Rust Analyzer is that it will auto import the use for you. You have SIF64, but I don't just want the thermodynamic temperature, I want to use everything inside. Okay, this is what I normally do. Okay, or maybe I'll just leave it as thermodynamic temperature, then I'll add stuff as we go in. Now you can see that there's a problem because I'm returning a float value, a float 64 value or double value, but it's expecting a quantity. Okay, I found a floating point number, but this needs to be a thermodynamic temperature in a proper unit. So, well, that's one of the useful things that UOM actually helps you. it makes sure that you are returning the right units. So let me just put the variable temperature here, and let's say temp is a thermodynamic temperature. Okay, degree Celsius, and let's again put 5. If you code it like that, it should be correct. Let's quick fix it by putting the degree Celsius in there with the thermodynamic temperature, and you will be able to compile the code. Now, let's say there's a pressure, right? Let's say there's a pressure, and this is how you actually input pressure. Pressure new, and then maybe you put Pascal there. 1.01 E5. Okay, this is atmospheric pressure. Okay, pressure is not over here, so you need to import this. And Pascal is also not done, so you import it as well. All right, so anyway, the reason why I like to put star here is because I don't want to keep importing so many the units one at a time. It makes it very messy, so I just put star. That will import every single unit possible, every single quantity type possible, but not their units. You still need to import the units yourself. Okay, but of course you can leave it like that. You can use the auto fix thing to keep importing the quick fix thing to keep importing your pressure, import everything for you. That's totally fine. It just makes your code very messy, and I personally don't like that. But okay, let's say you try to return a pressure value. What will happen? Okay, if you try to return a pressure value, it will say that the units are wrong. Okay, the units are wrong. Okay, if the units are wrong, you will get an error and the code won't even run. Okay, so that's a great thing about the package. If you try to do this, it will not run because the units are wrong. Okay, so your code will only run if your units are correct. Okay, so you return the temperature, it's fine. You don't return temperature, it's wrong. And let's say you have another quantity and you try adding temperature and pressure together. You will also get a problem. Okay, again, wrong units. If they are added together, the code won't run. Okay, that's the great thing about the units of measure. Now, point of interest for you, units of measure is not only applicable to Rust. C# also has them, and C++ also has them, but yeah, C# also has them. You can go and you can try this if you want. Okay, it's not units of measure, engineering units. So yeah, any one of those statically typed languages such as Rust, C#, so on, you will be able to find some sort of a unit measurement kind of thing. So that's what you can do here, but I just want to let you know that that is a thing. Okay, not exclusive to Rust, but Rust has a good package for that. Anyway, back here, temperature and pressure, you try to add them together, the code will not run. So Rust, the units of measure package within Rust sort of handholds you, gives you guide rails, and prevents you from adding the wrong units together. So that's a great safety harness, so to speak. Okay, so let me delete this thing. Okay, so anyway, we'll come back here to our ideal gas.type. What did we want to find? Okay, so remember, if you wanted to find temperature, what do we need? We need the PV and we need the R, right? We need PV and R. So let's go and find PV and R. So here's a pressure. So we need a specific volume. That specific volume, okay, equals to volume. Well, you don't use volume. Maybe you use specific volume or molar volume. Molar volume is the correct one. Molar volume, new, okay. What units to get? I can't remember off the top of my head, so I'm going to search out the source code again. So maybe let's put 2.0 here. This is just a random thing. So if you don't put the if you don't put the volume here, here are some volumes you can actually use. Here's cubic meter per mole, cubic decimeter per mole, and so on and so forth. So let's put cubic meter per mole. All right, and let's actually import it. Okay, remember the quick fix button is as long as you just hover over, you should be able to get a quick fix button as what we saw in the last video. Okay, so this is the specific volume, and let's have a molar gas constant. That's the R, or maybe I'll just put it as R. So what's the units of R? Okay, what's the units of R? If you take a look at our ideal gas, okay, what are the units of R? Okay, so to answer that, let's take a look at the units of PV. This is in PV is usually, well, PDV. Yeah, PDV is a unit of joules. So PV is a unit of joules. Joules divided by N. This is joules per mole. Okay, so this is a joule per mole unit. Joule per mole divided by temperature is joule per mole per Kelvin. Okay, joule per mole per Kelvin. So let's jot that down. Okay. Again, we can use comments. R is in joule per mole per Kelvin, right? So what's a unit in joule per mole per Kelvin? Okay, I'll just tell you straight. This is actually entropy, right? Let R equals to entropy. So is there a unit called entropy or specific entropy? Well, let's take a look. All right, so let's look for joule per mole per Kelvin units. So I'm going to go here, UOMSI. I'm going to do joule per mole Kelvin, something like that. Okay, so what do we have here? Joule per Kelvin, joule per mole Kelvin, or let's look for entropy. Oh, we don't have an entropy unit here. So let's take a look. Maybe we have something like specific energy. I think I used this before. Okay, let me find it for you and then I'll show it to you. All right, after some searching, I found something suitable. It's called molar heat capacity. Okay, it's a calorie per Kelvin mole or energy per Kelvin per mole. Okay, if you look at specific entropy, it's also entropy per unit mass. If you take a look at what the units are, well, entropy is in units of joules per Kelvin, but now thank you Wikipedia, whoever's contributed there. But yes, entropy is in joules per Kelvin, but specific entropy, as in entropy per unit mass, or in this case mole, or molar entropy, this is in joule per mole per Kelvin. So it's in the same units as what molar heat capacity is here, so we can use that. Let's see whether we have a specific entropy here. Yeah, it doesn't seem to have a specific entropy just yet, but we can find the second closest thing is this molar heat capacity. So let's look at molar heat capacity. Okay, I'm going to just use the letter R or molar. Okay, let me use molar gas constant. Gas constant. Okay, equals to what shall we do? Molar heat capacity, new joule per Kelvin mole, 8.314. That will be it. Quick fix. Okay, and let's look at this universal gas constant. Okay, joule per Kelvin per mole. This is the correct unit. 8.31. Okay, 8.314. All right. So how do you return the temperature? Okay, I'm going to take temp equals to pressure, so P V divided by R, molar gas constant. Okay, and we don't really need this pressure right here. Okay, and again we run into the same problem, remember? We expected the trade temperature kind, but we got the trade kind. So remember, this molar gas constant actually has a temperature interval unit within it. And like I said before, we have to change those temperature interval units into what do you call that? You have to change it into thermodynamic temperature. So how do we deal with this now? Okay, pressure and volume is just an energy. There is no temperature there per se. The temperature comes from this molar gas constant. Okay, so this PV over R will give you the temperature in Kelvin or absolute temperature. So I'll just call this thing the absolute temperature interval. Okay, this is the temperature interval. Okay, and what? So this T here, this absolute temperature interval, this will be in a temperature interval unit. And like I said before, temperature interval units have to be distinguished from their thermodynamic temperature counterparts. But for now, the way we work around this is just, well, since PV is a energy unit and R is a molar gas constant, this absolute temperature interval will actually be the interval counting from absolute zero. Okay, it will be counting from absolute zero. So this absolute temperature interval is in Kelvin. Okay, let abs temp Kelvin value. So this is a float 64 value. All right, absolute temperature interval get Kelvin or UMSI Kelvin or temperature interval Kelvin. So this is starting from 0. Okay, this is starting from 0. And what I do is let temp equals to thermodynamic temperature new Kelvin, absolute temperature Kelvin value. And then there we go. That's how you return the value. Import Kelvin, make sure it's the thermodynamic temperature type, and you should be able to be fine. Okay, now we are having some other warnings, such as I forgot to add a semicolon. And that'll be done. Once the semicolon is done, this thing should be able to run. Okay, so there are actually a few ways of doing this part here, but I will not introduce all the ways of this temperature conversion. I'll just make it very explicit so that it's easier to understand. Okay, so this is how we deal with a simple ideal gas equation function, just like that. Okay, so this is a get temperature, but let's say you want to give you don't want to manually key in the pressure, and you don't want to key in the specific volume here all the time. Okay, so what can you do? You can give these two parameters as inputs. So what you can do here, instead of get temperature, you can get temperature based on a pressure that you give and a specific volume. Okay, just make sure it's the right units, molar volume, and that will give you the thermodynamic temperature based on the ideal gas equation. So let me just prefix this with ideal gas. RG. Okay, so I'll make sure it's in snake case for functions. So I'm going to just make this a bit neater. All right, so that's I guess it. I want to put this here. Yeah, that looks nicer. Okay, so this is how we actually do it. I can actually delete this two now because I can let the user or whoever input the specific volume and the pressure, and you'll get the ideal gas temperature. So let's just do some simple calculations with this. All right, how would you use this function? Okay, so what I was doing now is, well, basically when we had functions run before, there's no input and output. But now I'm making sure that there's an output. The output is thermodynamic temperature, and the inputs are pressure and specific volume. So this function is actually allowing you to give inputs and outputs. This is what functions normally do. Most of the time you'll have an input and an output, right? And it's the same for MATLAB as well, except now instead of just specifying values, you have to specify the type as well. If you come from a MATLAB background, okay, you have to specify the type as well. So pressure, you have to specify that it's a pressure type. The specific volume has to be a molar volume type, so that gives it the right units. The output must be a thermodynamic temperature type, so that we deal with this interval and thermodynamic temperature, you know, that kind of problem. Okay, so this will sort that part out. How do you call this function? We'll go to main. Okay, after the implicit Euler method is done, okay, let's say we have a volume, specific volume, and let's give it a molar volume of cubic meter. Okay, I can't even remember the units now. I just let the compiler suggest it for me. Let's just give it 1 meter cube per mole or something like that, or 1 dm cube per mole, 0.01. Okay, 1 meter cube per mole. That's a huge molar volume, I think. Okay, cubic meter per mole. Okay, I'm just referring to this right here, cubic meter per mole. And then of course, let's import this. And let's also have a pressure. I'll just have 1 atmosphere just for simplicity. Because too high pressure, you cannot really use the ideal gas equation. Pressure new atmosphere. And let's just do 1 atmosphere so that we don't have to type it out always in pascals. So the way to use our function, okay, you just call it get temperature ideal gas. Okay, so let's go here. Okay, sorry, pardon. Clear this out. Okay, let temperature ideal gas equals to get temperature ideal gas. We have a pressure and specific volume here. So that allows you, this is how you call your function. Temperature ideal gas, then you give it the parameters within the brackets, close it with a semicolon, and you're done. Okay, you scroll all the way down, you should be able to be fine. I want to print out the ideal gas temperature. Print line, temp ideal gas. Okay, better put a semicolon there. Okay, of course it will have a problem because you need to format the thing. So just follow what the compiler says, or you can use the debug. That's fine as well. Okay, what's the problem here? Standard format display not implemented for this. So I think the way to do it is put a colon and question mark, there. That will be able to help it to get it out. Oh yeah, look at this. Temperature is almost 12,000 Kelvin. Okay, that's a, like I said, this is a huge molar volume, so it must be very hot. Okay, the other way again, I really like this way is use the debug so that I don't have to worry about formatting. Okay. So look, temp ideal gas 1287.27 blah 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 blah. Okay, all that 2744 something something. Okay, so you'll see that there's a unit here. There is a 817. Yeah, 187. Sorry, 187. So that's how you sort of call functions, and that's how you use the units of measure. So this is example number 2. We have an ideal gas temperature equation. Okay, I'll stop for now, and maybe I'll see you next time. Goodbye.